Hey everybody. So here we are with a circuits problem, very specifically a superposition problem. All right. You've got this circuit, all right, there are two sources, all right? And they just say find the Vout, the output voltage with superposition, where the output voltage is what is attached to this 15 ohm resistor. Okay. Well, from a superposition point of view, Vout is equal to the Vout from the 0.15 amp source plus the Vout from the 10 volt source. Okay, I should just say VOI and VOV, but whatever. This equation is all we need to find Vout. So remember, each time I have a term in this equation that's going to correspond to a circuit that I need to solve, basically what I'm saying is as many sources as I have, that's as many circuits as I need to solve maximally. Okay, so I guess I'll do one in blue and one in green. So I'll say it like this. This would be VO from the 15, and this will be VO from the 10. There we go. So when it comes down to the 10, I'll say for IS, the current source. Draw it up. You draw the element, the source that has not been destroyed. All right, the source that has been not turned off is more effective to say haven't been destroyed. And you draw the resistors. Okay, so draw that. And it was connected as such. This was connected like this. This was connected at the top like that. All right. But then this voltage source is turned off. Remember, when a voltage source turns off, it leaves behind a short. Think about it like this. V goes to 0. When you turn something off, its value goes to 0. When I go to 0 volts, the only element that represents 0 volts is a short circuit, a straight line. Okay. This is what I have. This is what would be there without the presence of the voltage source. And what's sitting here is VO from the 15, the contribution of that voltage from the 0.15 amp source. Okay. Now, I've introduced a short. Just a statement that you should just remember. Whenever you introduce a short, always do a node trace. All right. Always do a node. I call it a node trace. Always do a node trace when shorts, empty lines, are established. Okay, so basically whenever you turn off a voltage source, you probably want to label the nodes. So I'm just going to call this A, this is going to be B, this is going to be C. Now, this is B, then this is B. This is A, then this is A, this is C, then this is C. Because remember, whenever you travel from, whenever you travel from node to node, if you have not passed by an element, then the node stays the same, all right? So B, as I go from this node to this node, there's nothing in the middle to stop it. Empty wire doesn't count, all right? It's not a real element. Because there's nothing to stop it, then it's going to stay as B. So with that being said, now that you know that, you can read what elements are between what nodes, and that's going to help you figure out what's happening. The 48 and the 16 are both between A and B. They are in parallel. What's got to be black? They are in parallel. 1, 2. Parallel. Okay, and in addition to that, this 60 and 15 are also in parallel. So with that being said, I can redraw this circuit, and I have not a voltage, bad habit. It's a current source, 0.15, and I have one here, B, and another one there. Okay, so this is going to be B, because B stayed constant, C, and A. Now 48 in parallel with 16. 48 in parallel with 16 is 12, right? 48 times 16 over 48 plus 16 is 12. 60 in parallel with 15 is also 12. Now mind you, the VO5, I could actually combine these two because ultimately the VO5 is not affected by the VO15, is not affected by a parallel connection because they're have the same voltage. Okay. So with that being said, I can find VO5 with some regular old Ohm's law. I can just say VO15 equals V equals IR, so it'll be I times by 12, where I in this case is the 0.15. 0.15 passes through both of those resistors uninterrupted like that. And it's following the proper sign convention. It's going to go from a plus to the minus. So this is going to be my answer. It's going to be 1.8. So one part is known. The VO15 has been found out. All right. Second part is looking for the contribution from this 10 volt source. So I'll do it here. I'll just say for the voltage source. Draw my voltage source, plus minus 10, resistor here, resistor here, resistor here, and resistor there. That one was ugly. And this is what we have. All right, 16, 15, 48, and 60, where this is my voltage from my 10. All right, and I do not draw anything to the right, to the left, excuse me, because when I turn off a current source, it turns into an open circuit. All right, a lot of people will draw leads like that, but honestly, you don't need to do that unless you're looking for the voltage source. Unless you're looking for the voltage between those leads are actually negligible. They're just dangling pieces that may confuse you when it comes to evaluating the circuit properly, honestly. Okay, so this is what we end up having when we look at the contribution just from that 10 volt source. Now, I'm going to tell you this can be solved. I want to find this voltage right here. You can use voltage divider. Use voltage divider. Now, why? A lot of people are looking at this and going, how in the world can you use voltage divider? Well, think about it. If I get rid of this piece right here, if I just hack it out, okay, I probably should have done that in black, but whatever. If I get rid of that piece right there, then this right here, this branch at the bottom is going to get 10 volts from the top to the bottom. Okay, so with that 10 volts, the 10 volts applied across both of these is going to give a certain amount of current. The current is just going to come from it because they need 10 volts. Okay, now even, let me just backtrack a bunch of times. Even if I do not get rid of, let me see if it'll do it for me. Come on. No, it's going to just take way too long. Even if I do not get rid of this side right here, okay, think about it. This side is also going to get 10 volts. So remember, this got an I associated with the 10 volts that it got. This side over here is also going to get an I associated with the 10 volts. But those two I's are not really connected to each other. All right, these need 10 volts, these need 10 volts. Honestly, this circuit might as well be a separate circuit from this one because the I that they get is purely dependent on the idea that they get 10 volts. This voltage source does not care about how much current it spits out. It only cares about how much voltage it can provide, which means if when it's connected to one thing, it can provide 20 amps, great. If it's connected to two things and it needs to provide 50 amps, great, whatever. As long as it can provide 10 volts, it's fine, all right? So because of that, this piece right here is effectively isolated. These are basically two circuits that are kind of touching, but can be solved from an isolated point of view. And because of that, because both of these get 10 regardless of whatever else is happening, I can just say VO from the contribution is going to be the 10 volts times by the resistor that I care about, 15, divided by 60 plus 15. Okay, that is going to be 2. Okay, so 2 volts is the contribution from the voltage source. So with that being said, I have the two pieces of my output. I can now just say, I guess I'll put it in black, try to get it over here. V out is just going to be the 5 piece, which is 1.8, plus the piece right here, which is 2. The answer is 3.8 volts. This is the voltage felt by that resistor. Okay, so just a couple tips. Just remember, when you're turning off these sources, current source turns into an open circuit, excuse me, because zero current corresponds to empty space. All right, a voltage source turns into a short circuit because zero voltage corresponds to an empty wire. All right, turn off each, whenever you're focusing on one source, turn off every other source. In this case, there was just 2, but if I had multiple, let's say I had 4, and I wanted to focus on the 10, I would turn off the 15 and everything else. Okay, so turn off for every individual source that you're evaluating, turn everything else off. And if you ever introduce, basically whenever you turn on voltage sources, you probably want to make a node trace to get a good sense of what your nodes are, because that really is going to tell you what's in series and what's in parallel afterward. Do not think after you turn off a source the circuit stays the same. No, the circuit in this case is completely different from the original circuit, and the circuit in this green case is completely different from the original circuit as well. This black circuit is basically this blue circuit and this green circuit happening at the same time, and that's the whole idea behind superposition. So do not lose those ideas. Superposition can be easy if you follow the pieces of it that, take the simple pieces and make sure they all make sense, or it can be very difficult because you're not, maybe you're not node tracing, or maybe you're not remembering to turn everything off properly and all of that jazz. So it's one of many to come. Okay, I hope this helped.